This presentation is titled Classification of EEG Data based on the Spatio-Tempororhythmic Characteristics of the Task-Discriminating Functional Subnetworks by Ali Haddad and Laleh Najafizadeh, Integrated Systems and Neuroimaging Laboratory, Department of Electrical and Computer Engineering, Rutgers University. The outline of this presentation will be as follows. First, we define functional networks. Second, we propose an EEG classification framework that uses functional networks. The three main steps constituting this framework are then discussed. These are the feature extraction, feature selection, and dynamic classification. Then the experimental data and the results generated by testing the proposed framework using that experimental data are given. And finally, some concluding remarks. Functional networks. A functional network is a temporary structure spanning a set of brain regions which show similarities in their activity patterns during the corresponding interval. The similarity suggests a collaboration among the involved brain regions on performing a common function. For example, the functional network in Figure 1 formed within the gamma band consistently during the right-hand squeezing, but not during the imagery of that action in our experimental data. Using functional networks for the classification of EEG. Through their association with certain functions, functional networks can provide information on the tasks during which they form. However, functional networks have been rarely utilized in brain-computer interfaces, or BCIs. We employ the spatial, temporal, and rhythmic features of the identified task-discriminating functional subnetworks in dynamically classifying the brain's functional state via EEG. Extracting the spatio-tempororhythmic features. First, rhythmic analysis. EEG is decomposed using wavelet, then inverse wavelet transform into 6 dyadic subbands. These are the low part of the delta subband, then the high part of the delta, then the theta, alpha, beta, and gamma subbands. The subband components are normalized for subband equalization and finally augmented into 6 band-specific sets of sensors. Second, temporal analysis. For an interval of time, let our functional networks stay active with common time courses or activity patterns given by the columns of matrix A, and average gain vectors which describe the cortex to sensor conductivities given by the columns of matrix F. Note that gain vector FR characterizes the location of the Rth functional network on the cortex. Taking background cortical activity and noise into account, the sensor space EEG data can be formulated according to the linear EEG model. A minimum mean square error estimate of the first term can then be found through singular value decomposition. The main aim of the temporal analysis is to break the augmented EEG data into intervals during which functional networks sustain their connectivity. Our source-informed segmentation algorithm uses the significant left singular space as an estimate of the span of average gain vectors F1 through FR. It monitors the augmented EEG data for indications on changes in the spatio-rhythmic distribution of functional connections. Third, spatial analysis. Augmented EEG segments are passed to the S-Loretta source localization algorithm to estimate the corresponding augmented cortical activity. Active functional networks in the cortex are characterized by their common time courses and intensity maps, that is, the intensity of every node in that network as given by the columns of matrix P. The augmented cortical activity can then be formulated using another linear relationship. Therefore, we can approximate the intensity maps in terms of the most significant left singular vectors of the estimated augmented cortical activity segment. The estimated intensity map of each functional network is thresholded to convert it to a Boolean map. A Boolean map indicates whether each node in the augmented cortex belongs to the network or not. Thresholds are calculated via a phase randomization-based Monte Carlo simulation. Overall, a variable length sequence of segments per trial produces a corresponding sequence of functional networks. Selecting the task-discriminating features. Let X and Z be the sets of Boolean maps of functional networks identified during Task 1 and Task 2 respectively. Find a small set B of Boolean maps of functional subnetworks that are associated more closely with, here interpreted as occurring more likely during one task than the other. We formulate estimating the Boolean matrix B as a Boolean matrix factorization problem. To solve this problem, we propose the discriminative-associative or DASO algorithm, which is based on assessing the cross-matrix differences in pairwise correlations among the occurrence patterns. For a feature vector sequence, the functional networks within the corresponding extracted sequence are projected onto the task-discriminating maps. Note here that projections of partial overlaps are real valued. The dynamic classifier. A dynamic recurrent neural network classifier is used with the extracted features. A classification decision is made at the end of each identified segment, starting with the first segment. The decision is then updated at the end of each following segment during the trial. We used shuffled trials with the following proportions. 75% were used for training, 10% for validation, and 15% for testing. Experimental data collection. We conducted a visually cued motor execution imagery tasks experiments. The tasks included tongue movement, up and down, and hand squeezing left and right hands. Each one of the 8 tasks included 45 trials. 8 subjects volunteered to our experiments. The EEG data was recorded using 128 channels sampled at 2000 samples per second. The extracted epoch constituted in the 3 seconds planning and execution imagery phases. Pre-processing included bandpass filtering and artifact removal using ICA. Results. We attempted 4 different motor execution versus imagery classification problems. Each one of these problems involved one of the previously described directions, that is, up, down, left, and right. For feature selection, 20 task-discriminating functional subnetworks were identified and employed. As can be seen, the proposed framework scored an average classification accuracy higher than 81% within 500 milliseconds of the presentation of the visual cue, which falls within the planning phase, and an accuracy higher than 84%, 1500 milliseconds after the presentation of the visual cue, which is within the execution imagery phase. We also examined the classification accuracy around different time instants for a varying number of selected task-discriminating functional subnetworks K. The relatively high accuracy at low values of K demonstrates the versatility of the first few identified subnetworks in classifying the intention of motor execution versus imagery. Conclusions. We proposed a novel framework for utilizing the features of functional networks in the dynamic classification of the brain's functional state via EEG. The framework extracted information about the location, the dynamics, and the subband of the activity patterns of the identified functional networks. For improved decision-making, the most task-discriminating functional subnetworks were identified, then used for feature selection. An average classification accuracy above 81% within 500 milliseconds of the queued task planning phase before the execution imagery phase demonstrated the utility of the proposed classification framework. Thank you for watching.